Okay, so let us begin once again with a quick recap. Okay, so the last thing we spoke about was probably the Viterbi decoding algorithm. Is that the tail biting, maybe collection of miscellaneous topics around convolutional codes. A couple of things I want to highlight is this notion of trellis. Of course, trellis plays an important role. Nudge. அங்க வருது. Okay, so the trellis is an important idea. Okay, so if you think about convolutional codes, you have to immediately think about the trellis, right? That's the main idea. Okay, everything around the convolutional code revolves around the trellis. Okay, everything about convolutional codes is about the trellis. It plays an important role in decoding, of course. Okay, it also plays an important role in understanding the structure of the encoder. And we did not really spend too much time on this, but things like, for instance, minimum distance, the way I loosely define minimum distance is definitely quick to, when we can find that out using the trellis in a much faster way than you would in any other way. Okay, so things like that are interesting. And another interesting idea which has gained a lot of prominence because of turbo codes is this recursive systematic encoding. And there are several encoders, all of them are equivalent in the sense that the same set of code words are produced anyway. So they do not make any difference to the decoding performance if you look at convolutional codes as their own, as on its own, okay, as one entity. But it turns out in turbo codes and other constructions, you use convolutional codes in concatenation. Okay, when you use them in concatenation, the structure of the encoder makes a difference, okay, and we will see that soon enough. But for that reason, the recursive systematic encoder is particularly crucial. Okay, so the properties that are interesting when you go to recursive systematic encoding is low weight code words do not necessarily always, low weight messages do not necessarily always give you low weight code words. Okay, so in particular, weight 1 message definitely gives you a very long code word, okay, and weight 2 also most of the time gives you long code words. Okay, only in some cases it gets stuck into a multiple of the polynomial that you use for the connection, and then in that case it works out to a low weight code word. Okay, so that is the main ideas that we spoke about, and then of course the Viterbi algorithm. This is the ML decoder for convolutional codes, and what we are going to see next is called the BCJR algorithm. Okay, so let me try and see if I remember the names of Nek, maybe EK and Ravi. Okay, so the Viterbi algorithm is the soft ML decoder. This is the bitwise MAP decoder. Okay. So it is named after the 4 inventors, okay, and we are going to describe the BCJR algorithm in this lecture. Alright. So just like the Viterbi algorithm, the BCJR algorithm also works on the trellis. Okay. While the Viterbi algorithm makes one pass through the trellis from the initial stage to the final stage and outputs the most likely code word or path on the trellis, that is what it outputs. Okay. What the BCJR algorithm does is it will make 2 passes on the trellis. It will go once from first to last and then from last to first, and for that extra effort what you get in the bargain is not only do you get, well, you may not necessarily get the best path, but what you get is what, a posteriori log likelihood ratio for each message bit. Okay, that is what you get from the BCJR algorithm. Okay. So, which is what the bitwise MAP decoder does, right. What is the difference between ML and MAP? Okay. ML, you just find the code word which is closest in Euclidean distance, and bitwise MAP, what should you find out? You get the LLRs for each bit given all the received words, received information. Okay. So, it is a bit more information, and that plays an important role in the turbo decoder, etc., etc. Okay. So, if you were to only decode convolutional code and nothing else, what will you go with always? Go with Viterbi, you do not need anything else. But if you want to decode the convolutional code as part of a larger system, you might want to use a bitwise MAP decoder, because it produces what is called soft output. Okay. It produces probabilities on the bits, not just the likely bits itself, and those probabilities can be used further by another part of your decoder which wants to improve, etc., etc. Okay. So, that is the idea. Okay. So, let us talk about the BCJR algorithm. Okay. So, we'll pick a rate half 0 terminated convolutional code, convolutional encoder. Okay. So, that is what we will do, and I mean, of course, the BCJR algorithm is more general than just rate half codes. 0 terminated, yes, everybody assumes 0 terminated, but rate half is not definitely needed for BCJR algorithm, but it is easy to describe, and I will use rate half. Okay. So, what will happen if you use rate half is your message, I have been using M or U for message, M, U maybe, right, U. Okay. So, you have one, you have let us say k message bits, U0, U1 all the way to UK minus 1. Is the AC really on? I think it's really hot. It's on, is it? I think I'm going to be extremely unpleasant at the end of this lecture. Okay, let's see. Okay. So suppose you have a message U, this is going to get encoded by the convolutional encoder. Okay, like I said, it's rate half. So you will get code word. So let us just say code word is C. So I get C0. Okay, so I think V is what we use for the code word, right? We use V or C? V, maybe V. Okay, so I'll use V again. V, I probably put V1, V1 0, is that right? This is what I did. V2 0, this is how it is. Okay. So this is the first stage, and then for V1 1, V2 1, all the way to V, it's going to be K plus mu minus 1, right? So I'll once again take memory to be 2. Okay. It's just again convenience. Of course, it doesn't work. It of course works for everything else. So in that case, the last stage will be K plus 1, right? So it goes up to K plus 1. Okay, so that's going to be the code word, and then we'll do BPSK encoding, BPSK modulation. Okay, and what comes out I'll maybe call Y. Okay, Y. Once again Y01, so on all the way to Y K plus 1. Is that okay? So what's going to happen to this Y? This will go through an AWGN channel, which will add a noise vector Z, and you will get a received vector which we will call maybe R. Okay, I don't know, this doesn't. R1 K plus 1, R2 K plus 1. Is that okay? So this is the setup for the BCJR algorithm that I'll be using. So of course, there's you can use it in a much larger setup than this. The BCJR algorithm, just like the Viterbi algorithm, works on any trellis. If you have a trellis, BCJR algorithm would work. Okay, so I am giving you a much simpler situation. So for instance, a standard place where you might again use it is in equalization. If you have an ISI channel and you have a trellis corresponding to that, you can once again use the BCJR algorithm. Nothing stops you from doing that. So as long as you have a trellis, you can use the BCJR algorithm, but I am going to use this specific example to make my life easier with notation and other things. Okay, so once again the crucial thing is the trellis. So what are all these notations in a trellis? If I look at the nth stage of a trellis, okay, there will be a corresponding trellis and that will have 4 states, right, because I have assumed memory is 2. If the memory is not 2, then you will have a larger number of states. I am just drawing, I am drawing one particular example. Okay, so you can in general have a different situation. Okay, in the Lth stage, we are going to associate with the Lth stage several things. First of all, U sub L is the input corresponding to the Lth stage, and of course this is not known at the decoder. Okay, so the decoder has to estimate this. Okay, and the output corresponding to the Lth stage is of course known to the decoder, R1 L, R2 L. Okay, these are the received values. Okay, received values corresponding to, okay, something went wrong with my values. That is better. Okay. So these are the received values corresponding to that Lth stage. Okay. So and there are some I guess some connections, does not matter how they look. Okay, so I will just draw some arbitrary stuff here. Okay, so this is how the trellis connections look. Okay, it does not matter how the connections are. Okay, so as far as the decoder is concerned, everything is a random variable, right? UL is a random variable. Okay, it does not know UL. Okay, it only knows RL1 and RL2. Okay, it does not know UL. This would be a random variable at the receiver. Okay, so the goal in a bitwise MAP decoder is to compute probability of UL equals 0. Okay, let us say this is the goal of bitwise MAP. Okay, so but usually nobody computes the probability directly. What do you compute? You compute the LLR, right? So that is what you compute. So well, actually I am wrong in saying this. So let me just take this back and then write down exactly what the receiver wants to compute. Of course, you want to compute probability that UL is 0 given the entire received vector R. Okay, so this is what you want to compute. If you do not give the received vector R, of course it is half or something. There is no big deal in that question. Okay, so given the entire R, okay, but you do not compute this probability directly. What do you usually compute? You compute the log likelihood ratio. Okay, so let us say we will just keep it like this for now. Okay, it does not matter what it is. We will go to the LLR later. We will try to compute this probability that UL is 0 given R. Okay, so UL, like I said, this is the input. This is a random variable at the receiver, and for that you want to compute the probability. Okay, so let us add a few more random variables to describe what is actually happening. Okay, so we will say the state before the Lth stage. Okay, so we will call that as some random variable. Okay, so what can be a good notation for that? So we will say it is, let us say S, capital S, L minus 1. Is that okay? Does it seem okay to you? Okay, so we will say the state before the Lth stage, but then the problem will come when you do 0th stage, right? So let us maybe S L minus 1 is not a good idea. We will do SL. Okay. SL is the state before Lth stage of trellis. Okay. So what will be SL plus 1? It will be the state after the Lth stage, right? So that will be again random variables. Okay, so SL is definitely a random variable at the receiver. It is not known. Okay, So there will be probabilities, okay. So there will be probability that SL equals 0 0, probability that SL equals 1 1, etc., etc. So any for any particular state there will be a probability that will happen, okay. So what we are going to do is we will try and write this conditional probability in terms of SL also. We will bring in the states, okay. So why do we bring in the states? It is of course the most natural thing to bring in the trellis. We know ultimately that the states contribute to the decoder a lot, okay. So what happened in the Viterbi decoder clearly was because you could retain just one path per state at a given stage, right. So the states are going to play a crucial role. So it turns out likewise here in the bitwise MAP decoder also the states will play a crucial role in facilitating the computation, okay. So we have to bring that in. So before that, okay, since anyway we are interested in the LLR, it is enough if you compute f of r given UL equals 0, okay. So the reason is, I mean, if you do the LLR kind of computation, you will see that there will be some a priori probability coming in, but then that is definitely half ahead of time. So it will all going to cancel, and this calculation you will be really trying to compute f of PDF of r given UL is 0, okay. So that is also good enough. So keep that in mind. So we might equivalently try and compute. So I will use P just to make sure that I do not get into trouble here. R given UL equal to 0, okay. So in fact this given UL equal to 0, you can even say this is as good as trying to compute probability of r comma UL equals 0, right, because what is the relationship between the conditional one? You are dividing by probability of UL equal to 0. So that is also the same thing, okay. So this is again equivalent to trying to compute probability of r comma UL equals 0, okay. So we will try to actually compute this guy r comma UL equal to 0, okay. So that is the one that we will try to compute, and then you will see that LLR is basically log of P of r comma UL equal to 0 divided by P of r comma UL equal to 1. So anyway for LLR you know this is good enough, okay. So if I do this for UL equal to 0 and UL equal to 1, then I am done, there is no problem, okay. So that is what we will do, okay. So let us try and concentrate on this and see how to simplify this, and then we will maybe also simplify probability of r given r comma UL equal to 1, okay. So we will see that is also easy to simplify, okay. Okay, so how do you simplify this guy? Probability of, let me write UL equal to 0 comma r, okay. This now I am going to bring in the states, right. So this is the same as summation over, okay, all states S prime comma S such that what, okay. So I will write that down, and before that I will write this here, okay. So probability of SL minus 1 equals, no, SL equals S prime comma SL plus 1 equals S comma R, okay. So I want to break this expression up in as a summation over possible states S prime comma S, okay, and I want to say SL should be S prime and SL plus 1 should be S, okay, small s and small s prime, okay. So what should S prime and S be, okay. So let me ask this question, okay. So basically the condition here will be that the branch S prime to S should be labeled with UL equal to 0, that is all, okay. So it should be labeled with input 0. Is that clear? Okay. So when I say UL equal to 0, there are out of the 8 branches, there will be 4 branches which correspond to UL equal to 0 in the trellis, right. There are 8 branches, 4 of them will correspond to UL equal to 0, the other 4 will correspond to UL equal to 1. So I am only going to look at those branches where UL equal to 0 happened, and then look at the starting state and the ending state, okay, and then let S prime and S vary over those starting states and ending states, and then I can write this probability as the summation of this probability. Is that okay? So if I want to compute this guy, what I really need to compute is this fellows, okay. So we will compute this in the BCJR algorithm. For each S prime S. Is that okay? All right. So now it is also clear what will happen if I want to compute probability of UL equal to 1 comma r. How will this change? So you have to do the summation for S prime S labeled with input 1, that is all. Okay. So all I really have to do is compute what is inside this for all possible transitions S prime comma S. Okay. If S prime to S is not connected by an edge, I do not have to compute this, so you cannot really compute this, it will be like 0. Okay. So no problem, you do not have to compute it, but if a transition is possible from S prime to S, I have to compute probability that in the nth stage SL was S prime, SL plus 1 was S, and the vector R was received. Okay. So remember, this P that I have written here will be like a complicated distribution, it will be neither discrete nor continuous kind of distribution, right. So it is a little bit, you have to be careful when you deal with these things, but usually this is a very simple problem, so it is not a big concern. Okay. So do not ask me what this P is it a PDF or a PMF? Okay. So it is some distribution, okay. It is a valid way of writing it. You can write it with CDF if you like, but this is a much simpler way of writing it, and hopefully it is clear to you. Okay. Alright, any questions about this? Is okay? Alright, so this is what we will try to compute, probability that in nth stage the previous state was S prime, the next state was S, and the vector R was received. Okay. So once you compute this, anything else you want to compute is done. Okay. So how do you go about doing that is the question. Okay. So for that we once again use the trellis property, and how in a trellis you naturally have several Markov chains, all your random variables will become Markov chains. Okay. So that is the crucial idea. Okay. Given that you are in a particular state in a particular stage, all the past is totally irrelevant for the present and the future. Okay. So that is the crucial property that is exploited in computing this. Okay. So that is why this becomes easy. Okay. So we use Markov chain properties of the trellis to now simplify this expression. Okay. So there will be a recursion that is developed, and that will what will help you. Okay. So it turns out the main result or theorem or lemma or whatever it is the following relationship. You can show, is a simplification of this, you can show probability that SL equals S prime, SL plus 1 equals S, comma entire vector R can be written as, let me make sure I don't make a mistake here, there are enough ways of making mistakes here, can be written as a product of 3 terms. Okay. And these 3 terms, it is very common to call them alpha, gamma, beta. Okay. So what are the 3 terms? The first term is alpha L minus 1 S prime, the next term is gamma L S prime comma S, okay, and then the next term is beta L S. Okay. So one can show that it can be written as a product of 3 terms. Okay. So like I said, this is the main result, and this result will naturally give you the algorithm. Okay. So of course I will tell you what these alpha, beta and gammas. Okay. So if you just write it down like this, then you can say these two are 1, and then this becomes, it is not the point. Okay. So the point is, you can write down, you can say that this alpha L minus 1 of S prime, this will be probability SL equals S prime, comma R, but R between 0 and I have been writing it from 0 to L minus 1. Okay. So L will not be involved. Okay. So when I write 0 to L minus 1, what it means is, if I have a vector indexed from 0 to whatever, if I say 0 to L minus 1, you only take those indices. Okay. So it is like MATLAB notation, it will be R of 0 colon L minus 1, that is not actually MATLAB notation. Why? 0 is not a valid index in MATLAB, but anyway, it does not matter, think of it as MATLAB notation and vectors. Okay. So R from 0 to L minus 1. Okay. And then what is gamma? Gamma L of S prime comma S is once again probability that SL equals S, comma RL 1 RL2. Okay. So that is hopefully clear. Okay. What I mean by RL1 RL2, that is the output at the Lth point, given that SL minus 1. Okay, did I make a mistake here? I think this is SL minus 1, I am sorry. Oh, no, it's SL, it's SL, sorry. Next one will be SL plus 1. Yeah, you're right. This will be SL plus 1 given SL equals S. Thanks for pointing that out. SL equals S prime. Okay, and then beta L of S, the Americans say it beta L of S is going to be probability R. Okay, so 0 to L minus 1 was involved in the alpha expression, L was involved in the gamma expression, and in the beta expression you are going to get, okay, you are going to get Windows doing something. Okay, so R L plus 1, hey man, it really wants to do something. Okay, what did I do? It wants me to go to next page. Now I want to finish this off and then we'll see. Okay, L plus, see it continues to think that I am writing something, so I do not know why. Okay, L plus 1 all the way to the end. Okay, so the end is going to be what? K plus 1, no? K plus 1 given S L plus 1 equals S. Okay, I managed that quite well. Okay, so this decomposition is possible because of the Markov properties. Okay, so we will call on a lot of Markov properties to enable this this decomposition, and you might wonder what is the big deal in this decomposition. You haven't learned anything new. I mean, it's not like anything has changed. Okay, so we had one probability expression and there is some product of three things, and each of them involves anyway a long vector of R. Maybe the second gamma expression does not scare you too much. Okay, so there is only one L that is involved, but alpha and beta both of them involve long vectors R. Okay, so is there any simplification is a natural question you can ask. Okay, so we will first do the simplification, this decomposition, and then I will show you that it is possible to write down recursions for alpha L minus 1 in terms of alpha L minus 2 and gamma L minus 1. Okay, and then it is possible to write down recursions for beta L in terms of gamma L plus 1 and beta L plus 1. Okay, so once you have recursions like that, you can recursively compute alpha and beta very efficiently. That is the point. Okay, so just decomposition itself is not anything special. It becomes special because of the recursions that are possible for alpha and beta. Okay, you might be able to write so many other decompositions using the Markov property, right? So why not? But this particular one is nice because the recursions that are possible. Okay. Which noise? Let me see. I will write it down. You will see. We will assume. Yeah, I think so. Yes. Yeah. So for this decomposition, yes. Okay. So let's see a quick proof of this. Okay, the proof is not too hard. I mean, it's quite straightforward. Just that the notation is a bit clumsy, but it's quite easy. Okay, so SL equals S prime, SL plus 1 equals S, and then the entire vector R. This is what I want to write down, right? And I want to use some Markov type property. Okay, so the first step is to first write down. Okay, so instead of writing SL equals SL plus 1 equals, I will simply write S prime comma S. Okay, so when I say the first thing is S prime means SL equals S prime. The second one is S means SL plus 1 equals S. Okay, so just to make my notation simple. Okay, I will first simplify split R as going from 0 to L minus 1, and then the RL. I will write RL. So RL is basically these two guys together is denoted RL. Okay, all right. The two outputs you get in your L stage denoted RL. RL, and then I will have R L plus 1 to K plus 1. Okay, now you start gathering things which are in the past and in the future, and then do some conditioning and see what happens. That is the idea. Okay. So this you can write as probability of R L plus 1 to k plus 1 given everything else. Okay. So everything else is what? S prime S R L R 0 to L minus 1. Okay. Then I should multiply by all these guys, S prime S R L and R 0 to L minus 1. Is that okay? So now what is an immediate simplification in the first term? Okay. So remember, like I said, noise is IID. Okay. So the noise is not dependent on the past, and given that S L plus 1 was equal to small s, all other information you have is totally irrelevant to R L plus 1 to k plus 1. Okay. It does not matter what happened in the past, as long as you got to the state S in the L plus 1 stage, I mean after stage L, only that matters. Okay. So in the first term you can clearly drop this one and this one. Okay. So you can drop these things. Okay. So now let us look at this guy. So here I am going to now write it as times. Now once again, what is the most recent thing in this? RL, right? RL is the most recent. So let us write it as, and S prime S also, right? S and RL happen at the last stage. Anyway, from you guys are all experts in reworking the solution, so you can look at the solution. So you need to get RL given S prime R 0 L minus 1 times what? Probability of S prime R 0 L minus 1. So now once again you use your Markov thing and say, if you are at S prime before the Lth stage, all these guys do not matter in S and R. Okay. So that is totally determined only by S prime. So I can conditionally make it independent. Remember, these are all conditional independences, they are not totally independent. Okay. Only given all these things, the thing becomes independent. So now we have the final form and we can easily write it. I will write this last term first, because that is what gives me my alpha term. P S L equals S prime comma R 0 to L minus 1 times P S L plus 1 equals S comma R L given S L equals S prime times, what is the last term? R L plus 1 to k plus 1 given S L plus 1 equals S. Okay. So like I said, it just uses basic chain rule and probability and the Markov condition with the trellis. Okay. The trellis plays a key role, as you can see, so it is important. Okay. So actually if you have any Markov chain, okay, this BCJR computation will apply. Okay. So if you have any Markov chain where the state is hidden to you, okay, so you can think of it as a hidden Markov model if you want. Okay. The state is hidden to you, what you observe is a noisy version of something that denotes the state transition, okay, which gives you probabilities for the state transitions. Okay. Any such situation you have, you can use the BCJR algorithm. Okay. So only property you are using clearly is the Markov property, nothing else matters. Of course, the independence of the noise from time to time also is used. If the noise were dependent, clearly I can't throw out all of these things. Okay. All right. Okay. So that is the proof for the main result. So once you have a proof for the main result, the problem of computing this term becomes equivalent to computing alpha L minus 1, gamma L, beta L. Okay. So how can we compute each of those things is the question. Okay. Gamma L is the easiest thing. Okay. I will do that first because it involves only values in the state, in the Lth state. Okay. Alpha and beta we will need recursions. Okay. So there is a very easy recursion which you can once again derive for alpha and beta, and you can write that down very easily. Okay. Is that clear? Seems confusing? No? Okay. So it is also good before we do all those things to see this formula in the trellis, so to speak. Okay, so how do you see this formula in the trellis? Okay, in the L stage you are going to have alpha L minus 1 or what, L minus 1 0, this will be alpha L minus 1 1, right. Those will be the probabilities that you can associate with those states, alpha L minus 1 2, alpha L minus 1 3. Okay, and here with these states what will you associate? Well, not alpha also you can associate, but that does not play any role in the Lth stage, right. So what is most natural? Beta, right. You can do beta L 0, beta L 1, beta L 2 and beta L 3, okay. And then you might have some transition, so this might be 0, this might be 1, this will be 1, this will be 0, okay. So for each transition, each branch you have a gamma, right. For each branch you have a gamma, right. So look at the gamma depends, alpha is associated with a particular state in the previous state, beta is associated with the next state. What is gamma associated with? Both S prime and S, which means it is associated with the branch, okay. So on each branch you can put a gamma, okay. So the gammas will come here, okay. So let me just put the whole thing there and say gammas, okay. So how do I compute the final probability, this probability? How do I compute this probability? This guy, how do I compute this guy on the trellis? If I take a particular branch, I multiply the alpha on the left hand side and the beta on the right hand side with the gamma in the branch, okay. So I take each branch, I take the alpha, beta, multiply them with the gamma on the branch, I get the probability that I want, probability of S prime comma S comma the entire vector R, okay. Is that clear? So how will I compute probability of R comma UL equals 0? I compute this quantity for all the branches corresponding to 0 and then add them up, okay. So it is the same thing. For probability of R comma UL equal to 1, I compute the probabilities, the products for all the branches corresponding to input 1, then add them up, I get that, okay. So clearly the crucial thing is alpha, beta and gamma, and they are all naturally associated with the trellis nodes, okay. So of course you are also right, there is alpha L on this side also, okay, but then that is for the next stage, right. So valid only for the next stage. I am not going to use that alpha in this stage, okay. So it is more natural to think of alpha from on the left and beta on the right and gamma on the branches, and my basic probability of the branch given the comma the entire received vector is basically the product of alpha, gamma and beta, okay. That is how you think of that product. The product is the probability of that branch comma the entire received vector R, okay. So I add up all the branches together which have input 0, I get the probability of R comma UL equal to 0, etc., etc., okay. So that is crucial. So now how do you efficiently compute alpha and beta? So you have recursions, okay. So alpha beta recursions, okay. So the first formula, so to speak, is this formula for alpha. You can show alpha LS is summation over all S prime gamma L S prime comma S alpha L minus 1 S prime. Okay, remember this is capital L, capital SL, L plus 1, right. Okay, so this is SL, did I get that right? Yeah, okay. So there is like a shift in the way this notation goes, and this guy, okay, S prime comma S is from SL to SL plus 1. Is that okay? Okay, I am not going to prove this recursion, it is not too difficult, it is basically based on the expression for probability. What is this? There is this expression, this is probability of S comma, yeah, S L plus 1 is S comma R from 0 to L, right, that is this expression. So basically what you have to do is once again use Markov property. I want to use alpha L minus 1. So what I will say is the first step you can easily write down, it's maybe I will quickly do the proof here, we do have time. So you do summation over S prime probability of SL plus 1 equals S comma SL equals S prime comma, you split that as 0 to L minus 1 and RL. Okay, so this is the first step that you do, and then what is the next step? Okay, so you can see you can easily figure it out from the formula that is given there, S prime. I am going to now use Markov property. Is that okay? Okay, so I need an alpha here. Okay, so I am going to write. I am going to condition on that, right. So I am going to condition on that. I am going to write given SL plus 1 equals. Did I get this right? Yeah, SL equals S prime comma R0 to L minus 1. Okay, so I have to write down here SL plus 1 equals S comma RL times, I would have already got the alpha L minus 1 of S prime, right, that is it. And then this guy is basically, once you know SL is S prime, this you can drop and that becomes the gamma that I want. Okay, so it is basically the Markov property gives you this recursion. Okay, so once again it is interesting to look at this in terms of the trellis. Okay, so if you interpret it in terms of the trellis, this recursion looks a little bit artificial now. It seems like why do we do all this S prime etc. Remember, if you want to compute alpha L of S, the only S prime that is relevant is ones which lead to S. Okay, if you are not connected to the S prime, you do not have to include that here. So let me put this here, S prime such that S prime to S is an edge, is a branch. Okay, so it is a valid branch. Okay, I have to only take those things. I mean, if I could not have come to S from the previous state, there is not going to be any probability contribution from that. So I only have to take that. Okay, so in terms of the trellis, it is particularly easy to understand this. Yeah, definitely. I mean definitely only branches are considered. S prime to S is labeled with input. If it is not even a branch, it won't be labeled. Definitely it is a branch. Okay. So here once again the trellis interpretation for the alpha recursion is quite easy. If you look at alpha, let us say L of 0, okay, so this might be connected from here and then from here. Okay, there will be like a gamma 1 here and there will be a gamma 2 here. Okay, and this will be alpha L minus 1 of 0 and alpha L minus 1 of 1. And what will be this alpha L of 0? It will simply be alpha L minus 1 of 0 times gamma 1 plus alpha L minus 1 of 1 times gamma 2. Okay. When I write it as a formula, it seems like a very fancy formula, but essentially what I am saying is I know the probability of being in state 0 and state 1. Well, when I say it is not the probability of being at state 0 and state 1, right, the definition is probability of your state comma all the received values. It is not given. Okay, so it is not given, it is comma. Okay, it is and it is the joint probability. Okay, so given, so once I know these probabilities, how do I find alpha L of 0? Simply take that, multiply by the corresponding gamma that leads you up there and add it up with the other contributions that you have. So it is kind of like a natural recursion that you get on the trellis. Okay, right. There will be a very similar natural recursion for beta also. Okay, so maybe I'll do with something like this. Maybe this goes here and goes here. Okay, so if you want to look at beta L of 2 and then a beta L of 3. Okay, and if you want to compute beta L minus 1 of 3. Okay, and if this is like say gamma 1 prime, gamma 2 prime, what will this be? This will once again be the natural formula that this is beta L of 2 times gamma 1 prime plus beta L of 3 times gamma 2 prime. Okay. So I can write down the beta recursion more formally also. Okay, but this is what you have to remember. Okay, so this is how you can easily remember the recursions. Okay, otherwise it's, if you write down the Markov formula every time also you can do it, but it's a little bit more confusing. Okay, but this is a very easy way to remember the recursion. Okay, Once you know the gamma computation, the alpha recursions are and beta recursions are easy. Okay. So, how do you start the recursion? Okay, so any recursion has a starting point, right? What is the starting point for this recursion? Okay, so if this were the zeroth stage, then what do I know? Yeah, so you are always starting at the all zero state, right? Right. So only one state will be probable with probability 1, all the other states will be probability 0. Okay. So then what do? At the zeroth stage on the left you only put probability 1 for this and everything else 0. Okay. What about beta? Beta likewise have 0 terminated. At the k plus 1 stage, only the 0 terminated state, 0th state will have probability 1, everything else will have probability 0. Okay. So these alphas are also called forward state occupation probabilities. Okay, and this is a good word because it gives you a nice feel for what they actually represent. Okay. Forward state occupation probabilities. What is beta? Beta is, okay, so let me not write it there, write it there. What is beta? Beta is backward state occupation probabilities. So alpha is like the probability that you are in Maharashtra and beta is the probability that you are in Bihar. So that's the way, that's another way to think about this. Forward state, backward state, man, I don't know, too many people are puzzled by these kind of comments, but so that's the, so so when you go in one direction you can compute alpha, you have to go in the forward direction, and then computing beta you have to come back in the backward direction. Okay, so that's what you do. Okay, what about gamma? Gamma is neither forward nor backward. Okay, so it's in each stage. Okay, so it corresponds to the branch probabilities for each stage. So gammas are like branch metrics. Okay, is that all right? Let me make sure I didn't goof up on anything. Okay, it's fine. Okay, I don't want to write down a formal formula for beta. Okay, you know how it will look. How will this look? You simply change alpha to beta here, and then instead of L and L minus 1 you put L minus 1 here and L there, that's all. So you get the exact same, and S prime and S you have to reverse. Okay, so that's all. So you're going to get the same formula. Okay, so the last thing is gamma, and that's crucial, that's a little bit important. So let's see, I mean I want you to pay some attention here because it's it plays an important role in the turbo decoder and all that. So what's gamma? Gamma L S prime comma S is probability that, what is the formula? S L plus 1 equals S prime comma S L equals S, is that right? Comma R L, right? R L and given, okay, that's an S prime, okay, given S L equals S, is that right? Okay. So, okay, all right, I think, so many mistakes, that should work out right. So what's, so we have about a minute left, so I think, so let me stop here. Okay, so in the next lecture I'll pick up from here, I'll talk about how gamma is computed, and that will kind of conclude the BCJR algorithm.